So our definition of a metric space is that you have a differentiable manifold M. And in addition to this differentiable manifold, so the manifold, as I think Toshiba asked last time, if you have this manifold, then you also have, sorry, is there a question?
No, sir, that was a mistake. Sorry.
Okay. So if you have a differentiable manifold, that manifold admits tensors on it. Okay, you can have vectors and tensors and dual vectors, but it doesn't tell you about any particular choice of tensor or vector. It just says that you can have tensors and vectors. Okay, or it comes with a tensor space or a vector space. Now, a metric space is one where you pick out a particular 0-2 smooth tensor. Okay, and this particular 0-2 smooth tensor is, as we discussed last time, right? It's chosen from the space T20 of M. These are all possible tensors, smooth tensors on the manifold M, out of which you pick a particular tensor, which we denote like this. Okay, and that tensor is what we denote as the metric tensor. So if you specify such an additional metric tensor, okay, a smooth tensor, then you say that the space is a metric space. Okay, so now you've given some additional property to M, which is you specified a metric. So now the advantage of having such a metric is that it allows you to take dot products of vectors. Okay, so a 0-2 tensor takes two vectors as input and returns a real number. Okay, and therefore you can define the notion of dot product between two vectors. Okay, so therefore you can now, we discussed if you have an infinitesimal vector, that is in components, it looks something like this. So it's sort of an infinitesimal vector. You can think of this as generating an infinitesimal displacement. Okay, and now what we'll do is we'll supply such a vector to G, and it'll give a notion of distance associated with that infinitesimal displacement. Okay, so that's the idea that we're going to pursue today. And so now we'll get, and so once you have distances between infinitesimally nearby points, you can get distances on a curve, okay, by taking infinitesimal distances between points. Okay, so this will allow us to define distances on the manifold, okay, on a general manifold. So distances there's no concept of distances on a general manifold. Like for example, a sphere, I can rip it open, stretch it out, okay, do all kinds of things. I mean, the ripping open is not something that you can do, but within a coordinate patch, you can stretch out as much as you want. Okay, and so we already saw that when you just look at the sphere minus the north pole, if I stretch it out into a plane, then the distances get completely distorted. Okay, or in fact, there's no preferred notion of distance between any 2 points on the sphere. Okay, and our notion of distance that is associated with the sphere comes from how we think of it as embedded in 3 dimensions. Okay, so if you think of it as a regular sphere embedded in 3 dimensions, then you would have a specific notion of distance, and that notion of distance is coming from the fact that in 3 dimensions we think of the Euclidean distance between 2 points, that is the square root of dx square plus dy square plus dz square is the distance. Okay, but a general manifold doesn't have a notion of distance with it until we specify a metric tensor on the manifold. Okay, so now we'll define specifically what we mean by a manifold, and there are some properties that a metric tensor must satisfy in order for it to be a valid metric space, okay, according to some definitions. So we say that G must satisfy the following axioms at every point P. So for every point P on the manifold, it must satisfy these axioms. So the first axiom is that we assume that it's a symmetric tensor. That means if you supply it two inputs, U and V, in general, the order in which you supply inputs to a 0-2 tensor or any rank n tensor, the order is important. Okay, and if you change the order, you'll get a different answer when you supply them in a different order. But what we want is a symmetric tensor, which means if I supply UV or if I supply VU, okay, I change the order, I will still get the same real number. Okay, it's the same real number in either case. Okay, so it belongs to R. So this is what we call a symmetric tensor. Then the next requirement is that for a fixed V, okay, so if we take any fixed V belonging to the vector space V belonging to TPM, okay, and we put this V in here, and if GPUV is 0, okay, for all u's belonging to the same space. Okay, so what this means is you take a point P on the manifold, okay, you pick a particular vector V, and now you take the dot product of this vector V with some other, any other vector U, okay, in this vector space, okay, by this, okay, by taking GP of UV. And if that is 0, no matter what your choice of U, that can only happen, the axiom is that that can only happen if V is a 0 vector, okay. So if V is a 0 vector, that's the only way that V will always give you 0 as its dot product with anything else. Okay, any vector that is non-zero will give you at least some non-zero dot products. Okay, that is another condition that we assume is a property of the metric. It's a property of this GP. Okay, so in words, we can state this property as for any non-zero vector, there exists at least some non-zero inner products or some non-zero dot products. Okay, so now if you have a manifold M with a metric that satisfies these two properties, okay, these two properties are, one is that it's a symmetric tensor, and second is that the only trivial vectors, that is vectors which are 0, only those vectors always have zero inner products. There are no other vectors which always have 0 inner products. Okay. This is also called a non-degenerate metric. Okay, we'll see what this means for a what it means to be non-degenerate. But this property of a metric is called non-degenerate. Okay, so a manifold M plus a metric G which satisfies these two axioms. Okay, the axiom of symmetry and non-degeneracy. Such a manifold with such a metric is called a pseudo-Riemannian manifold. Okay, that's the name given to such a metric. Now, if we change this property, if we modify this property 2 a little bit, okay. So if we modify property 2, or we replace property 2 with this alternative property, that is that the dot product between any two vectors is greater than or equal to 0. Okay, so this was not a requirement that we were imposing earlier. We said that the dot product is 0 only for 0 vectors, is always 0 only for 0 vectors. Now what we're saying is that the dot product of any vector with itself, okay, is always a positive semi-definite. Okay, semi means it can be 0, okay, and definite means it's always positive. Okay, it's not positive or 0, it's never negative. Okay, and if this statement is true, and the other rule that you impose is that equality, okay, bit of this equal to 0. This only happens when U is a 0 vector. Okay, so this is called a positive semi-definite inner product. If you impose this rule is obviously more stringent because you're demanding that the dot product of a vector with itself is always greater than or equal to 0 unless the vector is a null vector. If you impose this rule, then you get another type of manifold called a Riemannian manifold. Okay, so Riemannian manifolds are a subclass of pseudo-Riemannian manifolds. Okay, pseudo-Riemannian manifolds are more general. Riemannian manifolds, you're demanding now that dot products of vector with themselves are greater than or equal to 0. Okay, so these are the properties that we demand for the metric G. So not just that it's a rank 2 tensor, but it's also a symmetric rank 2 tensor. And if you're talking about a pseudo-Riemannian manifold, it has this non-degenerate property. If you're talking about a Riemannian manifold, you impose this positive semi-definite property on the metric. Okay, so we'll see quantitatively what this means. Okay, all right. So now once you have a metric, okay, once you have this metric with these properties, now one thing that you can see, okay, and we'll show these properties, is the metric induces an isomorphism between vectors and dual vectors. Okay, that is for every vector V, okay, it maps me to a dual vector omega V. Okay, so this V belongs to the tangent space at the point P. Okay, and omega V belongs to the cotangent space. Okay, These vector spaces are the same dimensions, but they're different vector spaces. Okay. But once, and in general, there's no way to take a vector in TPM and relate it to a vector in TP star M. Okay. I mean, you can make a choice, but there's no preferred choice. Okay. All choices are okay. The metric gives you a preferred choice, okay, of this mapping between a vector in the tangent space and a vector in the cotangent space. Okay. Uh, so what is this choice? Well, let's go back and think about the definition of the metric. Okay. So the definition of the metric is that it's at some point P, it takes in two inputs. Okay. The inputs are vectors, so they belong to the tangent space, two vectors U which belong to the tangent space, and the result is a real number. Okay. That's what we mean by a dot product. Now, instead of thinking about it as taking two vectors as input, okay, let's pre-supply the metric with one of those inputs. Okay, so it's really, we're specifying the metric plus a vector. Okay, and we're thinking, so it has one slot open, okay, into which we can introduce a vector. So this object, which is the metric with one vector already inserted, okay, can be thought of as an operation, and this operation acts on vectors. Okay, and it returns real numbers. Okay, so this is a linear map. Okay, because tensors act linearly. Okay, so this object acts linearly on any vector that I supply over here. Okay, and this operation basically takes me from the vector space to real numbers. Okay, but we've already seen that dual vectors do exactly the same job. Okay, dual vectors, if I take any dual vector belonging to the cotangent space, the job of a dual vector is it takes a vector, okay, it takes a vector from TPM and maps it to a real number through this inner product, okay, omega P of V. So in other words, we can think of this operation, okay, as picking out a particular dual vector. Okay, so given a vector U and a metric, okay, you've got an operation now which acts on vectors, and this operation does exactly the same thing as a corresponding dual vector which belongs to TP star M. So you can just match this, or you can say that this particular object is a dual vector, and whatever this dual vector is, okay, we'll call it omega U to recognize the fact that this is a dual vector that corresponds to the vector U. Okay, so given the manifold now has a metric, okay, and now we're considering a specific point P on the manifold. At this point on the manifold, if you specify a vector U, I can also construct for you a dual vector omega U. Okay, so that is what a metric does. It allows you to map vectors to corresponding dual vectors. Okay, so given any vector U belonging to this vector space, it maps you to a corresponding dual vector. Okay, and this is one of the reasons why probably in your physics courses you're not familiar with the concept of dual vectors, is most of the time you are assuming the metric of space or space-time, and therefore there is no real distinction between vectors and dual vectors, because for any vector I can always construct the dual vector. So we never bother talking about the dual vectors, we only talk about the vectors. Okay, but as we've seen, the concept of a manifold is more general than the concept of a metric space. A metric space has a particular metric. Okay, and on a manifold there is no natural identification of a vector with a dual vector. Okay, it's only once you put a metric on that space that there becomes a natural mapping between vectors and dual vectors. Okay. Okay. So the one homework exercise for you is to show that the vector omega U, okay, is unique. That is, given a U, okay, which is distinct from a vector V, the dual vector that you get for U is distinct from the dual vector that you get for V. Okay, so that is, if you have U and V are two vectors, then omega U and omega V are distinct. Okay. And you need to use the axioms of the properties of the metric that we chose. Okay, Now, similarly, okay, instead of taking, so we said that there's an isomorphism, which means given a vector u, you get a dual vector omega u. But the reverse must also be true. That is, if I start with a dual vector, let's denote it as omega, I should be able to get a vector which corresponds to this, which I'll denote as u omega. Okay, so if I give you a vector, you are able to reconstruct for me a dual vector. If I give you a dual vector, you should be able to reconstruct for me a vector. Okay, and this is also easy to see how you can get, given a dual vector, how to get a vector that corresponds to it. Okay, you can yeah. So given a dual vector omega belonging to TP star m, you can find or you can induce a vector which corresponds to that omega belonging to the tangent space. Okay, and the way you do this is you say that we know how to evaluate the inner product of a dual vector with a vector. Okay, so this quantity is well understood. Omega u, okay, is a well-known quantity. So you demand that for any vector u, okay, you define a vector VW, okay, such that this vector also, if I use the metric to get the inner product, it gives me exactly the same result. Okay, and this should be true for any u. Okay, if you define it this way, then given a dual vector, you have basically found a vector, okay, which gives you exactly the same inner product. Okay, and therefore you've sort of made the reverse identification. Given a dual vector, you found the original vector that corresponds to it. Okay, so given a dual vector, now you can find the corresponding vector. Okay, so there is a perfect isomorphism, okay, or there is a mapping between a vector at the point P and a dual vector at the point P once you know the metric at the point P. Okay. Okay, any questions here? I'll pause for questions.
Hello, sir.
Yeah, Tarsha, go ahead.
Sir, is it possible, like for a manifold, to have two 0 to rank tensor fields satisfying the properties of the metric?
Is it okay? So is it possible to have two metrics, let's say, right, on the space? Is
Yes,
that the
sir.
question?
Yes,
Yeah,
sir.
in principle, yes. Okay, you can define it that way. So you're picking out two metrics, but then you don't have a unique notion of what is the right dot product, right? Is the dot product taken with the first metric or is it taken with the second metric? Which one are you talking about, right? So once you choose one as your preferred metric, okay, which is the one which I will use to define the dot products, then that becomes the metric of your manifold.
Okay, sir. So even like though even if I start with some G1, G2, they belong to the tensor space tau 20. But if I choose one, then that becomes the metric.
Right. I mean, so in a sense, every manifold has all possible tensors on it, right?
Yes, sir.
What you're doing is picking out one particular 0 to tensor and saying this is a special metric which I'm associating with this manifold. That's a metric space. And I'm
Yes,
going
sir.
to use this to define dot products.
Yes. So this 0 to tensor field that which follows these properties, that becomes the metric.
That becomes a metric, right?
Okay. Okay.
Any other questions? Okay. So we've seen the metric induces an isomorphism between vectors and dual vectors. So now there's a unique mapping between a vector and a dual vector. Okay. And this mapping is not there at the level of a manifold. Okay, it's only when you introduce a metric that there's a natural mapping between vectors and dual vectors. Okay, so we'll work it out explicitly for Euclidean space and Minkowski space in a moment. Okay, this mapping. Okay, so now let's consider a manifold M with a metric G. Okay, and let's consider some point P on this manifold, and let's consider a coordinate patch U, okay, which contains this point P. So there's a coordinate function phi, which gives me the coordinates of this point P as some x mu. Okay, so in the coordinate patch, so this coordinate, so I can imagine the space which corresponds to this coordinate patch. So this is phi of U. Okay, we can expand any 0-2 tensor in this coordinate patch in terms of the dual vector, the 0-2 tensor basis. Okay, and the 0-2 tensor basis is a tensor basis which you can form out of one-dimensional dual vectors. Okay, so you can take a tensor product of one-dimensional basis vectors, okay, or 1D dual tensors, 1D dual vectors. Okay, you can take a basis for those, and that basis we've denoted as dx mu. Okay, for every value of mu, you get one basis vector. Okay, in the dual vector space. And so if I take a tensor product of two of them, okay, that gives me a basis for 0-2 tensors. And now we take a coefficient, okay, g mu nu at the point P. So associated with this point P, this is the coefficient, okay, of this basis element. Okay, g mu nu P is the coefficient of this basis element. Okay, so this is the metric associated with that particular point P on the manifold. Okay, or this is the components in a coordinate system. These are the components for each value of mu nu. Okay, for each mu nu. Okay, how many such values are there now?
N each for mu and nu.
Yeah, so that's n square values. Okay, so for where n is the dimension of the manifold. Okay, so for each, so for example, for 4D space time, okay, n square is 16. So this is this g mu nu, there are 16 such coefficients. Okay, for every value of mu and nu, there are 16 such coefficients. Remember that this is not a differential coordinate change. This is a dual vector. Okay, this dx mu is a dual vector. This is also a dual vector, and this is the tensor product of those two dual vector basis elements. And these are the coefficients of those dual vector basis elements. Okay, and this is the metric at a particular point P. So this GP is the metric at a particular point P. In a coordinate basis, you can expand it like this. Okay, so once I know the particular coordinate patch, then I can write it like this. But remember that the concept of a tensor or the 0-2 tensor doesn't rely on any particular coordinate basis. You can write it in any set of coordinates. Okay, any valid coordinate patch, you can write it. Okay, so now what we can do is we can look, for example, at this GP. Okay, since it's a 0-2 tensor, we can ask how does it act on if I take vectors at the point P, which are basis vectors. Okay, so that is, I take partial x nu. This is a basis vector. This is a basis vector. Okay, so I supply these as inputs and I ask what do I get as the output? The output should be a real number. Okay, and the answer is that you will get, if I supply these two as the inputs, okay, then the output that you will get is just sorry. Yeah, so the output that you will get is just g mu nu p. That is, you will get that particular coefficient. Okay, the reason is gp. Okay, let's work this out. Partial x mu, partial x nu. Okay, so this is in a particular coordinate system. Now what we'll do is we'll write GP in terms of its coordinate basis entries. So we'll write it as G mu nu actually, but since we're using mu and nu here, we can replace the mu nu here with dummy indices. Okay, so we can change those dummy indices to alpha, beta, dx alpha, tensor dx beta. Okay, because these indices are summed over. These mu nu indices are not summed over. And now the first slot, this dx alpha, acts on partial x mu. Okay, so this acts on this. The second slot, that is this dx beta, this acts on partial x nu. Okay. And now, what is the action of this dual vector on this vector? What do we get? We've already worked out this inner product.
Delta alpha mu.
Delta alpha mu. And similarly, if you take this acting on this, you get delta beta nu. Okay, so you just get numbers, right? You get numbers. Okay, this is a real number. Okay, for every value of mu nu times, of course, this g alpha beta, and there's a summation over alpha beta. So finally, at the end of this, okay, if I sum over alpha beta, I'm just going to get g mu nu. So it's the mu nuth coefficient, okay, of g that I get. Okay, it's the mu nuth coefficient evaluated at the point P, okay, which is a real number. Okay, and since the first property of G is that we assumed it's symmetric, which means that if I change the order of these two, I should get the same answer. Okay, which means that, but of course, if I change the order of these two, I will get G nu mu of P. Okay, and these two answers should agree with each other. Okay, these two answers should agree with each other. So these are just numbers. G mu nu P are numbers for every value of mu nu. They should agree with the corresponding numbers nu mu. Okay, G nu mu P. Okay. So now usually we just omit the P. Okay, if you know which point you're talking about, okay, then you'll say that there is metric coefficients G mu nu evaluated at some point P in some particular coordinate system. Okay, so you know the point P and you know the coordinate system you're using. Okay, or if you want to be more specific, you say G mu nu at a particular point X, where this X refers to the coordinates of P. Okay, so sometimes in shorthand, we'll just write this as G mu nu at X. Okay, this is the metric coefficients G mu nu at the point X. Okay, and you know which coordinate system you're working in. Okay. So this is so this G mu nu at a given P, okay, this can now be regarded as a matrix. Okay, it's a matrix of coefficients, okay, of the metric G expressed in a particular basis, the basis of dx alpha, dx beta, or sorry, dx mu, dx nu. Okay, so these are now basis coefficients, and these basis coefficients are numbers. And now you can regard this as a matrix, okay, for values of mu and nu like this. Okay, you can regard this as a matrix, and the entries are G mu nu. Okay, mu labels the row indices, nu labels the column indices. Okay, so you can think of this as a matrix. And now the second axiom that we imposed, okay, the second axiom that we imposed was that G acting on any, so for a pseudo-Riemannian manifold, we said that if you have a fixed vector V, okay, the dot product with any u is equal to 0. Okay, if this is equal to 0 for all u, this can only happen if V is a 0 vector. Okay, so in component language, what this means is if I look at the coefficients G mu nu, it tells me that this matrix G mu nu has maximal rank. Okay, because now I can regard the dot product of two vectors u and V is, so let's just work it out. Okay, so if I take G acting on two vectors u and V, in components, this is G mu nu, dx mu, dx nu, acting on, let me expand u in a coordinate basis, so partial x alpha, and let me expand V in a coordinate basis. It has some vector coefficients V alpha and partial x beta. Okay, and again, this acts on this acts on this. And what that gives me is, so we can just use the same rules that we wrote before, and what you'll just end up getting is G mu nu U mu V nu. Okay, so this will be the dot product. Okay, of two vectors U mu and V nu. So now we can regard, if we think of the entries of U as a column vector and V as a column vector, okay, and G as a matrix, then in matrix notation we can write this as either U transpose GV, okay, or since G is a symmetric matrix, we can write it as V transpose GU. Okay, either way works. Okay, and so this basically gives you a way to take dot products. Okay, this gives you a way to take dot products. Okay, so there's a preferred way of taking dot products. So remember last time when we were discussing, if you don't have a metric, there's no natural way to take a dot product. Okay, in the sense I could always take V transpose U and matrix multiply them, but that is assuming a particular choice of the metric G. Okay, that is assuming G is delta Ij. Okay, that is, it's an identity matrix in some particular basis. Okay, it may not be the identity matrix in some other basis. So you're making a particular choice of what this G is. Okay, and such a notion of G doesn't exist on a general manifold. Okay, it only exists on a metric space in which you specified what the metric is. Okay, so there's no natural isomorphism between vectors and dual vectors. So there's no natural way to take dot products unless I specify a metric. Okay, so this is really the important point. You need to specify the metric to take these dot products. Okay, so now the fact that this is, so if I take a fixed V, and if for all U this is 0, this is 0, okay, that implies that V is equal to 0. What we're basically saying is that this dot product, okay, is never 0 for non-zero vectors. Okay, so if I have a non-zero U and a non-zero V, the dot product in general, let me just take that back. Okay, so if V is non-zero, okay, so I have some non-zero vector, either this, I can imagine, you know, these different choices, okay, or this, then for all of these, okay, there exists at least some U with which this has a non-zero dot product. Okay, there exists at least some U with which this has a non-zero dot product, which means that the matrix G has maximal rank. Okay, that is, this matrix G mu nu has maximal rank because, for example, suppose I take this particular V, okay, and I want to say that with all vectors U, it has 0 dot product. Okay, that would happen if, let's say I had an entire, what do I want? Yeah, if I had all these entries were 0. Yeah, the last column was 0. Sorry, the last column or the last row? Yeah, the last column. Yeah, if the last column is 0 and all these entries are non-zero, okay, then this would give me 0 with when I take the dot product with something else. Okay, because every time I multiply this with this, I will always get 0. Okay, so basically the fact that you're basically saying that the columns of G mu nu, or equivalently the rows, since G mu nu is a symmetric matrix, the columns and rows, they cannot be all zeros. Okay, all the entries of one column cannot be zeros, all the rows cannot be zeros. Okay, all the entries in any one row cannot be zeros. So that is what you mean when you say G mu nu has maximal rank. Okay, so the second property, okay, the second property that we demanded for G mu nu is that it has maximal rank. Okay, that means that there are some non-zero dot products for every vector. Okay, so the moment I have one of these non-zero, okay, some A prime, then, for example, this dot product becomes non-zero. Okay, so there exist vectors for which I can take dot products which are non-zero. Okay, so for every vector, there have to be vectors with which every non-zero vector, there have to be vectors with which I can take the dot product and get a non-zero value. Okay, so that second property translates into the matrix G mu nu having maximal rank. Okay, a maximal rank just means that all the rows are linearly independent, okay, from each other. Okay, yeah, so sorry, I did this in a particular basis, okay, in which it turned out that one row or one column is non-zeros. But if you switch basis, the general statement is that the rows of G mu are all linearly independent. Okay, the rows and the columns are all linearly independent. Or another way of saying this is the determinant of G is non-zero. Okay, which means it has no zero eigenvalues. Okay, so these are all translations of the second property. So property 2 for pseudo-Riemannian manifolds. The implication of this property is that G mu has maximal rank. This matrix G mu, and which means that determinant of G mu is non-zero. Okay, or G mu is since G mu is a symmetric matrix. Okay, this comes from the first property. Okay, since G mu is symmetric, okay, you can always diagonalize it. It's diagonalizable. And the fact that the determinant is non-zero means that there are no zero eigenvalues. It has no zero eigenvalues. Okay, a matrix or a metric which has no zero eigenvalues is called non-degenerate. Okay, that is the dot products of vectors in general. Okay, for some v which is non-zero, it has at least one u with which it has a non-zero dot product. Okay, there exists a u. I don't know if this is the right symbol for there exists a u for which this dot product is non-zero. Okay, such a metric is called a non-degenerate metric. Okay, so if I diagonalize the metric, okay, then I will get a, b, c, d, and all the a, b, c, d will be non-zero. Okay, or alternatively, now that I can define the determinant, okay, since the determinant is non-zero or the eigenvalues are non-zero, I can define the inverse of the metric also. Okay, and the inverse metric is denoted symbolically using indices as G upper mu upper nu. Okay, it's denoted like this. And now, so the fact that G inverse G is identity, okay, is just written in component notation like this: G upper mu nu, G lower nu lambda, which is also the same because I can take the transpose of this and that would give me the same matrix. So G lambda nu and G nu mu. So taking the transpose of this, which I can regard as matrix products. Okay, so the product of G inverse with G or equivalently the product of G with G inverse. This is just delta mu lambda, which is the identity. Okay, and it doesn't matter whether I write it as delta mu lambda like this or delta mu lambda like this, the ordering of the indices, because it's still it's a symmetric matrix. The identity matrix is symmetric. Okay, so we also define the symbol determinant of G mu nu as just small g. Okay, we write it like as small g. Okay, and the determinant of the inverse metric, that is G upper mu nu, we write as 1 by G. Okay, so we write it like this, or equivalent. Sometimes we write it as just G inverse. Okay, it means this G raised to the power -1. Okay, it's a number. Okay, so the determinant is a number. Okay, again, this is evaluated at some specific point P on the manifold. Okay, so this number, the determinant of G, is evaluated at a specific point P on the manifold. Okay, any questions here? Okay, so now let's work out that isomorphism between the tangent vector space and the dual vector space. Okay, in these components. Okay, so we want to find a dual vector omega that is dual to some vector u. Okay, so we'll expand u in components. We'll write u as u mu partial x mu, and we'll write the dual vector as omega mu dx mu. Okay, so now this isomorphism between vectors and dual vectors means that we can find for every vector, that is every set of coefficients u mu at the point P, we can find a set of coefficients omega mu also at the point P, which are related to each other. Okay, and it's quite easy to see that what you would get is that the dual vector components omega mu okay, would just be G mu nu U nu. Okay. So this is what you would, these are the dual vector components that correspond to these vector components. Okay, or equivalently, you can use the inverse metric and you can find, given dual vector coefficients omega mu, you can find vector coefficients u mu, okay, for a vector that is dual to omega. Okay, so you can write u mu is G inverse omega mu. Both these definitions are equivalent. Okay. Okay, you can see that easily because in matrix notation, again, the dual vector, okay, is equal to G mu nu, is equal to G u. Okay, that this is what we mean by a dual vector. Okay, or equivalently, u is equal to G inverse w. Okay, that's what this equation is saying. Okay. But it's important if you write it in matrix notation like this. One important thing that you lose is because this is a column vector and this is a column vector. You lose track of the fact that these are vector components and these are dual vector components. Okay, so it's important to keep that distinction between what are vector components and what are dual vector components. And the index notation helps you with that. Okay, so if the indices of the components are upper, then those are vector components. If the indices are lower, then those are dual vector components. Okay, so rather than working with the matrix notation, it is preferable to work with the index notation so that you're clear about whether you're talking about vectors or dual vectors. Okay. Okay, now we can do what we set out to do, which is, so if we had, one reason why we wanted to define a notion of dot product is so that we could get distance measures on a manifold. So if we have a manifold M, okay, in the last class we discussed that if you have a point P and you have a vector V, okay, and if this V is, let's say, an infinitesimal vector, so in coordinates it's some dx mu, where these are now coefficients. This is not a dual vector. These are coefficients, okay, which are infinitesimally small coefficients, okay, where dx mu is some different small number in the x0 direction, x1 direction, x2 direction. So we can write it as coefficients of partial x mu. Okay, and so if we have some infinitesimal vector v like this, you can think of it as generating a flow which moves the point P with coordinates x mu to some other point Q which has coordinates, x mu plus this displacement dx mu. Okay, so we haven't discussed formally how to do this, but I just told you intuitively you can imagine this. Even though this vector does not live on top of the manifold, it lives in the tangent space. Okay, there's a notion of how you can think of this as generating a displacement. Now what we would like to do is, this is just telling you how much the coordinate has changed. But as we've seen, a change of coordinate does not tell you what the distance is that you have traveled in going from this point to this point. Okay, but once you have a metric, you will now be able to define a distance associated with this displacement. Okay, so we want to find the distance associated with the displacement of coordinates. Okay, the displacement of which I'll denote symbolically as these components. Okay, so with this displacement in coordinates, I want to know what is the distance that I cover on this manifold. That notion of distance requires that I have a metric on the manifold. Okay, once we have a metric on the manifold, what we can do now is we can take this vector v and we can take the dot product of it with itself. And when we take the dot product with itself, we get a notion of a distance, okay, or a square distance, if you like. Okay, so this defines a notion of a distance between the points P and Q, which are infinitesimally close to each other. Okay, so these are coefficients which are infinitesimal. Okay, it's I apologize for the fact that this we're doubling our use of notation, but as we'll see, this doubling of use of notation, there's a reason for this. So here these are not dual vectors. Okay, these are not dual vector bases. These are just coefficients, which are small changes in um, in x mu. Okay. Okay. So now what we'll do is we'll just plug in v. Okay, which is this dx mu partial x mu. We'll plug it in here. Okay, so x mu is dx mu partial x mu, and we'll calculate the dot product of v with itself. Okay, and we'll denote this as ds square. Okay, so this ds square gives me the displacement. Okay, sorry, the distance between the points p and q, which are infinitesimally nearby in some coordinates dx mu. Okay, and so now this gives me, so I'll plug in dx mu partial x mu. I'll plug in dx nu partial x nu. We already worked out how to do this dot product for general vectors. The end result is going to be that you get g alpha beta. These are components of alpha beta. Okay, and okay, so sorry, let me just clarify one thing. So this dx nu are coefficients. Okay, so I can pull them outside this dot product. Okay, I can pull them outside. So that's over here. So these are displacements. And this g I expand in a basis. So this g alpha beta, dx beta. Now these are dual vectors. These are not displacements. These are dual vectors. And what is left inside are partial x mu, partial x nu. These dual vectors bases act on these vector bases. Okay, so this acts on this. And the result of this dx alpha acting on this is going to be delta alpha mu. The result of this acting on this is going to be delta beta nu. And now when I contract that with the g alpha beta, what I'm going to get is g mu nu. Okay, I'm going to get g mu nu, and I'll have these displacements left over. So now these are displacements. Okay, and this is just a number. Okay, this is a number associated with that displacement in coordinates dx mu. Okay, so associated with the displacement and coordinates of dx mu, where I have a displacement in x0, x1, x2, x3, associated with each of those displacements, where each of these is a small number, I now have a notion of a distance that I'm actually traveling. Okay, and now you're seeing that this is kind of getting back to your special relativity notation. Okay, because now I'm just computing a number. Okay, this is not a dual vector, this is just a number. So, but sometimes we refer to this distance element between two infinitesimally nearby points. This is also called a metric. Like in special relativity, we call this a metric. Okay, where g mu nu is taken to be this eta mu nu matrix, where eta mu nu is this matrix. Okay. So strictly speaking, with our definition of what a metric is a 0-2 tensor. Okay, it's a tensor, which means it has some components and it has dx mu, dx nu, where these are dual vectors. Okay, but now if I act this on an infinitesimal displacement vector on the same infinitesimal displacement vector twice, okay, then I will get a number, and this is that number. Okay, it's the line element. Okay, or the distance measure along some displacement. Okay, is this idea clear?
Yes, sir.
Okay. Okay, now now let's come to some final properties of this metric. Okay, so one is we already discussed that the first axiom of the properties of the metric indicates that g mu nu is a symmetric matrix, which means also that it's not only is diagonalizable, but the eigenvalues are real. Okay, so when I diagonalize g mu nu, I will get real numbers as the eigenvalues. Okay, I won't get any complex numbers. Now we categorize manifolds with a metric, or we categorize metric spaces based on the properties of the diagonalized g mu nus. Okay, so a Riemannian metric, that is, if you recall the definition of a Riemannian metric, the dot products were always greater than or equal to 0. Okay, so in components, what that translates to, okay, is that all these eigenvalues, okay, the fact that this is a non-degenerate matrix means that these eigenvalues are all non-zero. Okay, for a Riemannian manifold, you're also imposing this additional property that all these eigenvalues of this matrix A, B, C, D, these are all strictly greater than zero. Okay, strictly positive eigenvalues. That is the condition for a Riemannian metric. Okay, so that is typically of, for example, the metric in Euclidean space, in three-dimensional Euclidean space, your metric would be something like this at all points in space in Cartesian coordinates. Okay, so in Cartesian coordinates, this is what you'd have, and therefore your displacements would be dx square plus dy square plus dz square. Okay, all these coefficients would be strictly positive. On a pseudo-Riemannian metric, okay, you can have eigenvalues which are either positive or negative. Either of those works. Okay, axiom 2 only prevents them from being zero. Okay, that is your metric is non-degenerate. So this non-degenerate metric does not have any zero eigenvalues, but A, B, C, D can be positive or negative. Okay, Riemannian metric, you're imposing a stronger condition. You're saying that these eigenvalues are strictly positive. Okay, so Riemannian metric is a subset of pseudo-Riemannian metrics. Okay, now, okay, so now what we've seen is, first of all, the dimensions of the manifold are equal to the dimensions of the vector space TPM. Okay, and this must also be the size of the matrix. So this dimension is n. The size of the matrix G mu nu is n by n. Okay, as we've discussed, right, for any tensor, okay, of type RQ, okay, it has n raised to r plus q components. So a 0-2 tensor will have n square components. Okay, so it has n square components, which is this G mu nu. Okay, so now this G mu nu, okay, we'll assume that, so it's n by n, okay, which means it has n eigenvalues. Okay, and out of these n eigenvalues, we will take in a general pseudo-Riemannian manifold, I of these will be positive and j of them will be negative. Okay, where I plus j is equal to n. Okay, so I of them will be positive, j of them will be negative. So now this pair, the number of positive eigenvalues and the number of negative eigenvalues, this is called the index or the signature of the metric. Okay. So in general, when you diagonalize the metric at one point P, okay, you will get a diagonal matrix. Some of the eigenvalues will be positive, some will be negative. You count the number of positive eigenvalues, that is I. You count the number of negative eigenvalues, that is J. And the total number of eigenvalues is N, because this is an N by N matrix. Okay. Now what you can do is, it is always possible to rescale your coordinates. Okay, you can always find a different coordinate system where I just rescaled my coordinates, such that in this new coordinate system, okay, G mu nu is just all these eigenvalues are rescaled, okay, to 1. Okay, so now it's 1, 1, 1, minus 1, minus 1, minus 1. Okay, you can always rescale your coordinates in such a way, okay, that you get something like this. And now, okay, your Euclidean metric, okay, your standard Euclidean metric or Riemannian metric, basically you have I is equal to D. Okay, so if you have a D-dimensional manifold, dimension of M is equal to D. This is what we denoted as N earlier. If it's D-dimensional, and all of the eigenvalues of the metric G mu nu are positive, okay, and there are no negative eigenvalues, then you'd say that the metric is a Euclidean metric. Okay, so in other words, it's in a diagonal basis, G mu nu is the identity matrix. Okay, that's what we call a Euclidean metric. A Minkowski metric is one which has d minus 1 eigenvalues which are positive and 1 eigenvalue which is negative. Okay, so that is minus 1, 1, 1, 1, so on. Okay, that is a specific case of a pseudo-Riemannian metric. Okay, and this Minkowski metric is also called a Lorentz metric. Okay, now there is an important theorem. Okay, so this signature was defined at a particular point. Okay, which is we said that at a particular point the number of positive eigenvalues and the number of negative eigenvalues, this is something. Okay, now the claim is that if I have a non-degenerate metric over the entire space G mu nu, then the signature of this metric at any 2 points must be exactly the same. Okay, that is the number of positive eigenvalues and the number of negative eigenvalues cannot change from point to point. If I have a non-degenerate metric, that is a metric which does where G mu nu, the components of G mu nu are of maximal rank. Okay, that is they're linearly independent or there are no zero eigenvalues. If at no point does the eigenvalue go to 0, then over the entire manifold the signature of the metric remains the same. Okay, and that's easy to understand. Okay, for a smooth metric, why that would be the case, because if one of these eigenvalues has to transition smoothly from positive to negative, at some point it must go through 0. Okay, and if your metric is non-degenerate, that will never happen. Okay, we're not proving it rigorously, but you can understand why this would be the case. So everywhere on the manifold, the signature of the metric must be the same. That is, if I diagonalize the metric at any point P or another point P prime, the number of positive eigenvalues and the number of negative eigenvalues will be fixed. Okay, over the entire manifold. Okay, so now if we take a Lorentzian manifold, okay, that is one with I is equal to d minus 1 and j is equal to 1. Okay, then the elements of the vector space fall into 3 classes. Okay, that is the dot product of 2 vectors no longer has to be just positive. Okay, like it is for Euclidean space. Euclidean space where the metric can be put in this form. So you can have positive eigenvalues, in which case you say that the vectors U are space-like. Okay, so if U has a positive dot product with itself, you say the vector U is space-like. If the dot product with itself is 0, then you say U is light-like or null. And if the vector U has a dot product which is negative, then you say U is time-like. Okay, so you can understand where this terminology is coming from, and we'll just work it out right now. Okay, so if we consider a manifold M with a metric G, okay, where G is Riemannian, okay, that is it is strictly positive, dot products are strictly positive, then such a manifold is called a Riemannian manifold. If you consider a manifold G which is pseudo-Riemannian, that is, it satisfies the property that not necessarily positivity of dot products, but non-degeneracy of the metric G, then such a metric is called the pseudo-Riemannian manifold. And in particular, if it only has one negative, the metric G only has one negative eigenvalue, then you get a Lorentz manifold. Okay. So if I take the possible metrics that I can have, I can split them into degenerate metrics, which have 0 eigenvalues, and non-degenerate metrics. If I have a non-degenerate metric, then such a space is called pseudo-Riemannian. Okay, and that means that I will have, in general, some number of positive eigenvalues, some number of negative eigenvalues. If there are no negative eigenvalues, then the space is called Riemannian. If there is one negative eigenvalue, then such a space is called Minkowski or Lorentzian. And for other possibilities, you get other pseudo-Riemannian manifolds. Okay, so if we do a couple of examples, okay, what is Euclidean space? Euclidean space in n dimensions. Okay, so normal Euclidean space that we think about is R3 with a metric in some particular basis, which everywhere in space can be put in this form. Okay, everywhere in space it can be put into the form 1, 1, 1. Okay, and in fact, there's a simple coordinate patch for Rn. Okay, which is directly mapped to R3. Okay, so the entire space is covered by one coordinate patch, and everywhere on that coordinate patch, okay, this is the metric if I use my standard x, y, z coordinates. Okay, and the line element therefore is just dx square plus dy square plus dz square. Now, Minkowski space that you're familiar with in special relativity is topologically, it's just Rn. Okay, topologically, the topology of the space is just Rn. Okay, so it's the same topological space as Euclidean space. Of course, we're considering 4-dimensional space-time rather than 3 dimensionals. Topologically, it's the same. The metric is different. Okay, the metric is -1, 1, 1, 1. Okay, and I can cover again the entire space by a single coordinate patch. Okay, so I can map it to a single coordinate patch. So every point on this manifold, R4, can be mapped to a point in R4 in the usual way. Okay, I mean, you can understand what this mapping is. You know, any point is mapped to some point in R4. And now the line element is going to be, so if I call my coordinates in R4, t, x, y, z, then the line element is going to be minus dt square plus dx square plus dy square plus dz square. Okay, you can imagine I'm working in units where either c is equal to 1, or I can write this as c times t as my coordinate. Okay, it's just a rescaling of my coordinate. Okay, so so basically the topology of the space plus the metric. Okay, and here we understand that there's a single coordinate patch. So it's possible to specify the metric over the entire coordinate patch. Okay, and say that it's equal to delta ij. And similarly for Minkowski space, you can specify over the entire coordinate patch and say that it's eta mu nu. Okay, and in some basis you've expressed it as eta mu nu. Okay, that basis is called your Cartesian basis. Okay, and this is the analog of Minkowski and Cartesian basis. Okay, so this is what we mean by Euclidean space. This is what we mean by Minkowski space. Okay. Now, the other thing is the fact that you are not familiar with this idea of dual vectors, and the reason is in special relativity or Euclidean R3, we start with the metric, right? You already know how to take dot products of vectors. Okay, we start with saying we know how to take the dot products of vectors. And once you know how to take the dot products of vectors, we've already seen that there's a natural isomorphism between vectors and dual vectors. Okay. However, in general relativity, okay, we don't know what the metric is. We're trying to solve for the metric. We're trying to find the distance measure between 2 points on a manifold. And we're trying to solve for the metric on a manifold. So it's important to keep the distinction between vectors and dual vectors clear, because before you impose a metric on the spacetime, these are different concepts and there's no natural isomorphism between them. Okay. So you can see exactly what vectors and dual vectors are. Okay, so so remember, if I said that these are dual vectors and these are vectors. Sorry. And the isomorphism between them was, suppose I want the components of omega mu, which are dual to the vector omega mu, which is dual to u mu. I'll take omega mu. The components of omega mu are g mu nu u nu. Okay. So now, if I'm using, if I'm in Euclidean space, then g mu, and in a Cartesian basis, then g mu nu is equal to 1, 1, 1. Okay, which means any vector which has components ux, uy, uz, the components of the dual vector, okay, corresponding to this. Okay, and the fact that you can define a corresponding dual vector is only because you already have a metric. So once I have a metric, the dual vector components omega mu or omega 1 will be just ux, omega 2 will be uy, and omega 3 will be uz. So that's why we never bother in three-dimensional space, Euclidean space, we never bother to make this distinction, okay, because the components are just related in this very simple way. In special relativity, we have a slight difference, okay, so we write the dual vector components as eta mu nu, u nu. So now if I have a vector u0, u1, u2, u3, okay, and I take eta mu nu, so that will be -1, 1, 1, 1. This gives me omega lower mu, so that gives me omega 0, omega 1, omega 2, omega 3. And this you can see is minus u0, u1, u2, u3. Or if you remember in the special relativity class, if we use a different signature, instead of 1 minus and 3 plus, we use 1 plus and 3 minus. Okay, then you get u0 minus u1 minus u2 minus u3. Okay, and this is exactly what we called a covariant vector. The dual vector is what we called a covariant vector, and the vector is what we called a contravariant vector. Okay, what we were secretly doing was we were writing the components of a vector. Okay, and we were calling that a contravariant vector. And we were writing the components of this covariant vector using the components of the contravariant vector and lowering the index via a nu to a mu. Okay, this lowering of the index, it seemed to be just a mathematical thing. It didn't seem like it had any deep meaning. Okay, the deep meaning is associated with the fact that if I don't have a preferred choice of metric, there is no isomorphism between the dual vectors and the vectors. Okay, once I have a preferred metric, which is this eta mu nu on the manifold, okay, then the dual vectors or the dual vector coefficients are defined in terms of the vector coefficients. So it's just the covariant vector that corresponds to the contravariant vector. Okay, there's a natural mapping from a contravariant vector to a covariant vector. So if I had, for example, a momentum 4 vector, I could find its covariant momentum 4 vector. Okay, this is the dual 4 vector. Okay, or the components of the dual 4 vector. Okay, so it didn't seem like it was physically meaningful. Okay, but now we understand why. Once you have a metric, then it's just there is a natural isomorphism. Okay, between the two spaces. Okay, but the distinction between what is a vector and what is a dual vector, that distinction is real when you don't have a metric on the space. Okay, is this clear?
Sir, is there any special reason why we just didn't call them vectors and dual vectors when we did STR?
Well, the reason is it's just simple, right? I mean, you have to introduce the notion or the machinery of, a vector space, and then you have to define what you mean by dual vector space. And it's unnecessarily complicated, which is why typically when you're introduced to STR, you don't worry about this distinction. Just like, when you do Euclidean space, I mean, right away here, you could have been introduced to the notion of dual vectors, right? But it seems, redundant, right? If you're just trying to learn about Euclidean space. Okay, it's only when you go to these different levels of mathematical abstraction. Now, the reason is, why would you ever go to the level of abstraction where you don't have a metric? And there, in GR, it's natural to talk about spaces which don't have a metric because you're trying to solve for what the metric is on space-time. Okay, so what is the space on which you're solving? That space is a manifold, and the manifold has both vectors and dual vectors, and there's no natural way to map between them. Okay, so since you always had a metric given to you in STR or in Euclidean space, there was no real need to talk about the distinction between dual vectors and vectors.
Yes.
Okay, any other questions?
Sir, just like one question, sir. So like as you said, in general relativity, we are like trying to find what the metric is. We don't have like we're solving for the metric. So, so sir, like if we just want to write the dual vector, so we'll just have to write that in terms of notation, like omega mu s g mu nu omega nu, and then we have to work with that.
Yeah, you can write it like this, and you're trying to figure out what G mu nu is. Okay, so what you're saying? Okay, so basically you'll make a distinction between the manifold before I have a metric and the manifold after I pick out a specific metric. Okay, when this becomes a metric space. Okay, and what we'll do is, okay, you can imagine this manifold as having many possible metrics. Okay. Even if you have many possible metrics, the vectors and dual vectors are the same. Okay, but the mapping between vectors and dual vectors changes if I have this metric versus if I have this metric versus if I have this metric. Okay, and what we're going to do is when we solve the equations of general relativity, we're picking out one particular metric. With that particular metric, you have one particular mapping between vectors and dual vectors. Okay, but to formulate the equations of general relativity itself, it's good to keep the notions of vectors and dual vectors separate, because we're trying to talk about solving for different metrics on the manifold.
Yes, yes. So after like getting the metric, then we can talk about the corresponding dual vectors and vectors.
Yeah.
Okay.
Sir, I have a doubt regarding this. So in the above discussion, we indirectly reduced the generalized possibility of many metrics to one, right? Uh, for the above discussion, we only considered the metrics which generalize the Euclidean or the Minkowskian norm.
This one or this one? We're talking about here?
Yes, yes, sir.
Yeah.
Sir, no. So I mean, if sir, okay, sir, I'll think about it and like frame the question and ask in a few minutes. I guess.
Okay, sure, sure.
I'm not able to.
Other question? Okay. Okay, so you see that basically we need a lot of structure, right, in terms of starting with topological spaces. Then we take topological spaces which have smooth charts which connect them. Then you get a manifold. Manifolds have both vector, then you can define vectors, dual vectors, and tensors on these manifolds. Okay, but there's no preferred choice of any particular vector or dual vector or tensors on this manifold. But if I now add a particular 0, 2 tensor, and I say that this is a specific tensor which is, it gives me some properties, it allows me to calculate dot products on this manifold, then that becomes a metric space. Okay, and so so we have these varying levels of abstraction in which we think about space. Okay, topological space, you're just thinking about points and their connections. Okay, and the continuity properties of the space distinguish one topological space from another. Manifolds have this additional property of smoothness. Okay, when you deform one manifold into another, the deformation must be smooth. Okay, not just continuous. That means infinite derivatives in a coordinate system. You should be able to take infinite derivatives of coordinates. And metric space has this additional property now where there's a particular special tensor which allows you to define dot products. Okay, in general relativity, we'll assume that we are given a manifold. Okay, so we don't know what the manifold is. Okay, we don't know what the manifold is, but we'll assume that there's some manifold given to us. And on this manifold, we are trying to figure out what is the metric. Okay, that's sort of going to be the goal of trying to find some equation which tells us what the metric is. If we solve that equation, we'll find the metric. Okay, and that will tell us the way to calculate distances on that space. Okay, and as we'll see on curved spaces, the metrics in general have to be non-trivial. Okay, if your space is non-curved, then in some coordinate system, okay, you can always, in Euclidean space or Minkowski space, these are what are called flat spaces, or flat space times. We'll define the notion of what we mean by curvature and not. Right? At the moment, we don't have a way to understand what curvature means, but but in a flat space-time, you can always change your coordinate system so that in a particular coordinate system, you get this Euclidean metric, okay, or you get this Minkowski metric. and that is standard special relativity. But now what we'll try to do is we'll find general curved manifolds, okay, and curvature will be defined only when you have a metric. Okay, only when you have a metric, and we will try to find out what is the metric, okay, or what is the change in the metric because of curvature. Okay. All right. So now before that, what we'll try to do now is we'll talk about metric spaces themselves. Okay. So in a sense, so if you have a curved space, okay, so imagine a sphere with a metric on it. So now imagine the standard metric, okay, which is due to an embedding in R3. So now the distance measure on the sphere, if I put polar coordinates on this, okay, so some theta and some phi. Okay, then ds square is just going to be d theta square plus sine square theta d phi square. How did I get this? Well, you can show that in 3 dimensions, if I have polar coordinates r theta phi, then the distance between 2 points which are at r theta phi and at r plus dr theta plus d theta and phi plus d phi. Okay, I could work it out in Cartesian coordinates, and I know that the distance will be dx square plus dy square plus dz square. Alternatively, I can work it out in polar coordinates, and the same distance, okay, in 3 dimensions between any 2 points will be dr square plus r square d theta square plus plus r square sine square theta d phi square. Okay, if you've not worked this out, then I encourage you to do this. Okay, to work out this kind of expansion, you just have to use the relationship between polar coordinates and Cartesian coordinates. Okay, now what you do is you restrict yourself to a sphere, okay, which is a 2-dimensional surface. So r is fixed. So let's say r is equal to 1. We're fixing on a unit sphere, and you're not varying dr. Okay, so you're not varying in 3 dimensions. You're varying on 2 dimensions on the surface of the sphere. So in 2 dimensions, okay, this is called an induced metric. Okay, the fact that you are embedded inside 3 dimensions and you preserve distances on this 2-dimensional sphere, okay, which are actually a distance is in the 3-dimensional embedding. Okay, that gives you an induced metric. Okay, that metric has ds square is equal to d theta square plus sine square theta d phi square. So this is a particular choice of metric that you can choose by doing what is called an isometric embedding. Okay, where you don't distort distances on the sphere and you embed it in three dimensions. Okay, and this gives you a notion of distances between 2 points on a sphere. Okay, but this is a particular choice of a metric that you can impose on 2 sphere. You can impose other choices, okay, of metrics on a 2-dimensional sphere, okay, with general coordinates theta and phi. Okay, so this is a particular choice of metric on the sphere, which is induced from embedding it isometrically inside 3 dimensions. Okay. Yes, okay. So now basically what we're going to talk about is, now we'll assume that we know a metric. Okay, so for example, on a sphere, we know a metric. And now we want to talk about vectors. Okay, so vectors in a tangent space at some point P and how to move them. Okay, so right now what we said is the tangent space at the point P and the tangent space at the point Q. These are unrelated to each other. Okay. So the next thing we're going to do is talk about how to move a vector from one point here which is in a different tangent space to a vector in this tangent space and to compare these vectors with each other. Okay. So what we're going to talk about next is this idea of parallel transport of vectors on a metric space. Okay. Before we talk about parallel transport on a metric space, we'll talk about parallel transport of vectors first on a manifold. That is on a manifold without a metric. Then we'll discuss the specific case of a metric space. Okay, once you have a metric, then there's a particular special way in which you can move vectors from one point to another. Okay, so that's what we'll discuss next. Okay, so I'll just start it and then we'll continue the discussion next time. So the idea is that on a manifold M, okay, so now there's no metric on the manifold. Okay, so no metric. I have a vector v1 which is at the point P. I have a vector v1 prime which is at the point Q. Okay, And the vectors or tensors at the points P and the point Q, they live in different spaces. They live in different vector spaces. This vector V1 lives in the space TPM. The vector at Q lives in a space TQM. Okay. And so you have to be careful when talking about the derivatives, partial x mu, you're defining partial x mu at the point associated with the coordinates of P, versus you're talking about partial x mu associated with the x mu of the coordinates of Q. Okay, so these mean, so if you're not careful about this, then you're not clear about which point you're talking about, and therefore you're not clear about which vector space you're talking about. Okay. Now these vectors, okay, vectors give us a notion of directional derivatives, okay, when they act on smooth functions f. So as we've already seen, if I have some smooth function f on the manifold, I can think about, if at a point, I can think about the directional derivative of f in, let's say, some particular direction. And so if I have a vector v here, okay, we've defined a notion of v at some point p acting on f. Okay, and that defines a notion of a directional derivative of f along v at the point P. Okay, and we define this by talking about curves through the point P. So what we'd like to do is define a similar notion of directional derivative, but instead of these directional derivatives acting on functions, okay, these functions, you can think of them as scalar functions. They return a number for every point on the manifold. What we'd like to do is define some notion of derivatives or directional derivatives of some smooth vector field W. Okay, so if I have a smooth vector field W, what it means is that at every point on the manifold, I have a vector W, okay, a vector W of P, let's say at some point P, okay, and WQ at some point Q, and this vector field is smooth. Okay, I'm picking out one particular vector at every point on this space. That is a smooth vector field. And now what we'd like to do is define a notion of a directional derivative. Okay, so that is, as I start at the point P and I move from the point P to the point Q. Okay, how much has the vector at the point Q, how much is this different from the vector at the point P? Okay, we'd like some way to compare these two vectors with each other. So sort of an intuitive notion, okay, of what we mean by a directional derivative is we define some derivative, and this derivative means we have to specify a direction from point P to some neighboring point Q. So it's a derivative along some direction V. Okay, so we have to specify the direction along which we're taking this derivative. And we have to define the vector field W, okay, which is a vector field over the entire space, okay, of the vector W. And we have to define at which point we are taking this derivative. So we're taking the derivative at the point P. Okay, so I'm defining it at the point P. And roughly speaking, the way we'd like to define it is in the limit that this displacement from P to Q goes to 0. Okay, we'll write it as some epsilon. In the limit that epsilon goes to 0, we want the difference between WQ, which is this vector, and the vector WP. Okay, so we want to take the difference between these two vectors and to see how much this vector has changed, okay, when I compare it to this vector. Okay, roughly this is what you would think of as a directional derivative of a vector field. Okay, so it's the derivative of the vector field W along the direction of the vector V. So we're specifying one vector and taking the derivative of the vector field W, but we're taking the derivative of the vector field W at some point P, at some specific point P. Okay, this is roughly how you think of defining the notion of a directional derivative of this vector field at a point P. Okay, it's important that you specify this direction. Okay, the analog of this for functions was we took the derivative of a function f, a smooth function f, by acting it with it directly by a vector v. Okay, and this action was well defined, and that's how we used, in fact, to define, we used that action to define what vectors are. Okay, roughly speaking, we're now thinking of the action of a vector v on another vector field w. Okay, or rather than a function, okay, or a scalar function. Okay, and we're just denoting as grad v of w. Okay, we could have easily denoted this also as grad v of some f. Okay, some derivative of f along the direction v. Okay, except this is now a vector field. Okay, and this is now a smooth function. Okay, so we want to generalize this notion to taking directional derivatives of vectors. Okay, now there's one very obvious problem with this definition. Okay, this definition of WQ and WP, which is that these two vectors live in different vector spaces, as we've discussed. This lives in the vector space TQM. This lives in the vector space TPM. And so there is no natural way to subtract these two vectors from each other, because how do you compare these vectors? Okay, if you want to compare these vectors, okay, you have to sort of put them in the same basis. But the basis of this space is it's a completely different space from the basis vectors of this space. So how would I even begin to compare them with each other? Okay, so WQ is at point Q. So WQ belongs to TQM. However, the WP belongs to TPM. So it doesn't make sense to add or subtract these vectors which are in different vector spaces. Okay, there's just no way to compare them. What we need to do is we need to find a vector in TQM. Okay, we need to find another vector in TQM that, roughly speaking, corresponds to taking this vector WP, okay, from the point P and moving this vector forward, okay, to a point in the vector space TQM. Okay, so if I draw a picture, we have WP, we have WQ. What we want to do is take a vector WQ prime, okay, which is another vector at the point Q, which roughly speaking corresponds to moving this vector forward along the direction V, okay, so that it is now some vector WQ prime in this vector space. Okay, we need some intuitive notion of how to do this. Okay, so we need to find a vector in TQM that corresponds to WP. Okay, so in some sense there is a correspondence between this WQ prime and this WP, and our intuitive notion is, okay, if I have a vector field like this, to move this vector from here to here, we will parallelly transport it. Okay, so you think about this vector WP, which is here, and this vector is WQ. I will parallelly transport this vector. So I'll try to keep it at the same place. So keep it parallel to itself. Okay, and move here. Okay, and I'll call this WQ prime. So this is the parallelly transported WP. And now I can take the difference between these two vectors. Okay, and so I would redefine my notion of this directional derivative, this derivative along V of the vector field W, by taking WQ but not subtracting WP, but rather subtracting this WQ prime. Okay, this parallelly transported WP. Okay, and so the difference between these two, so if I have a vector WQ and a vector WQ prime which belong to the same vector space, then I can understand what the difference is between the two of them, and I can find the difference between these two vectors. Okay. So what we need to do, which we'll do in the next meeting, is to define this notion of how to parallelly transport. Okay, how to parallelly transport a vector WP to another point on the manifold WQ prime. Okay, at the moment there is no obvious way to do this. Okay, intuitively we are used to the idea of parallel transport, but that notion of parallel transport really requires a metric. Okay, as we'll see. Okay, without the notion of a metric, there is no obvious way on a manifold in which you can define the notion. You can define a notion of parallel transport, but that is a choice that you make. Okay, there's no natural choice. Okay, so what we'll do is first describe what do we mean when we say parallel transport and what is the choice that we're making. Okay, when we talk about parallel transport. And then what we'll do is we'll see that when you have a metric on the space, there is a natural choice of what we mean by parallel transport. Okay, there's in fact a unique choice of what we mean by parallel transport under some definition. So, so then what we'll do is for metric spaces, we'll know exactly what it means to move a vector from one point to another. And not surprisingly, that definition of how we parallelly transport will depend on the metric. Okay, it'll depend on how on the metric. And so in a metric space, there's a natural notion of parallel transport. Okay, on a manifold, you have to define what you mean by parallel transport, and there are many possible definitions, okay, of or choices of how you parallelly transport. Okay, so next time we'll talk about those choices, what those choices are for manifolds. Okay, before we talk about metric spaces. Okay, we'll stop here. Any questions you can ask?
Sir, I think that there are actually like some part missing in the notes about metric spaces which you have uploaded. Like it starts at
lecture 11.
Yes, sir. I mean, in the one that you've uploaded on Teams, every like.
Let me just see if I've covered everything here.
Sir, it starts from G mu nu at a given P can be regarded as a matrix.
Yeah, here.
Yes, sir. So I think there is like some discussion before that that's not there in what there.
You mean all of this is not there?
No, sir. This is not there.
This part.
Yes, sir.
Oh, okay. Okay, let me just review what's on Teams and then I'll try to upload this corrected version.
Yes, sir. Sure.
Sir, I think like when we download it as a PDF, it crops out because in OneNote it's like it's one long page,
Yeah,
right?
yeah.
That I think if we view it in MS Teams, it shouldn't be a problem.
Yeah, I think that is an issue. So it's basically one long page. So if you open it in something like Adobe, you won't see the whole thing, just because of the way Adobe processes it. But if you open it in Teams, you can scroll through and you should be able to see all of this. Can you just try it?
Yes, sir. Okay, I think in Teams it is in fact showing up the whole thing. So
yeah. I mean, this is just an artifact of how OneNote converts to PDF.
I use another PDF reader and it works fine with that.
Yeah, I've noticed I've not had a problem with other PDF readers like Sumatra or something. These are also free PDF readers. So, or Evans, I think should be okay. Adobe, I think the problem is that it requires some page size and so it crops out.
yes, sir. I think I can figure it out. Thank you.
Okay, any other questions?
Sir, I have a question. Sir, can you go to the next slide, the new slide?
Lecture 12?
Yes, sir.
Yeah.
Yes, sir. Sir, like as we are moving, as we are like doing this along V, this this derivative along V. So as we are going along V, that is why we are then only we will get to this point Q, right? If it was
Yes.
some other vector, we would have got to some other point Q prime.
Right. So the vector defines which is the point you're moving to. So if I have a vector V, then I'll move to this point. Okay. And then I want to take the derivative of the vector W along this direction V.
Yes, sir. But sir, does this vector V belong to TPM?
It belongs to TPM, yes.
Okay. Yeah.
Right, because remember that we talked about any vector belonging to TPM, we can think of it as generating a displacement.
Yes. Okay. Like choosing this direction, like we are choosing a particular direction. Like if we choose a different vector, then we'll go to a different point, neighboring, close to P.
Yeah, close to P. Yeah. Basically, you think of this as some infinitesimal vector. Okay. And along that infinitesimal vector. But also if this, so one property that we'll demand for the derivative is that even if we scale this vector up by some large amount, okay, this derivative is linear. Okay, so that basically the derivative, so even if I scale V by some amount, lambda, okay, so something like this, then the derivative will just be lambda times this. Okay, we'll assume this property of the derivative.
Okay, sir.
Okay, and actually in general, this lambda can be position dependent. So you can think of this as a function on the manifold. So for any function, this derivative we'll assume satisfies this property. Okay, so it doesn't even have to be an infinitesimal displacement. But V certainly tells you, like, if I think about an infinitesimal displacement, it tells me at least in which direction I'm taking the derivative.
Okay, sir.
Okay, so let's stop here. I'll just stop the recording.